Hi everyone. In this video, we are going to learn how to calculate the relative frequency. First, we need to understand what is a frequency distribution table before we can calculate the relative frequencies. Let's get started. As you can see from this document, um, when we collect data, usually the amount of data is huge. For example, if you want to poll people to see who's going to be next president, and you're going to poll at least thousands of people for their data to be reliable. So if you have that data in front of your eyes, all of the data, thousands, maybe tens of thousands in front of your eyes, you're not going to have any idea what that data tell you because there's too many of them. And that is the reason we need to organize data before we can extract useful information from those data. And the frequency distribution table is one way to organize data. So let's look at the definition of frequency distribution table. In your textbook, they just call it a frequency table. Basically, they're the same thing. And first of all of the frequency distribution tables have two columns. The first column is called category column. People also call it events column or value column. The second column is a frequency column. That means how many times each event occurs. You're going to put that how many times in the second column. Now let's illustrate this using a specific example here. Now let's say example, an insurance company determines vehicle insurance premiums based on non-risk factors. For example, how old the car is, how many miles you drive on average per day, and how old you are, your gender, your past record, accidents record, the make of your car, the age of your car, the color of your car, everything. There's many data points they need to collect so that they can feed those data points into their formulas to calculate a individual's premium. It's not everybody get the same premium. It's not. Let's continue to read this. If a person is considered a higher risk, their premiums will be higher, and that's common sense. One potential factor is the color of your car. The color of your car. The insurance company believes that people with some color cars are more likely to get in accidents. To research this, they examine police reports for recent total loss collisions. So everybody understands total loss collisions, right? After that collision, the vehicle is totally destroyed beyond repair. Okay, the data is summarized in the frequency distribution table below. Now let's look at the table as you can expect. And there are two columns. One column is about color. One column is about called frequency. And this first column is called category or events or value. Either way is okay. That's the general names. In this particular one, it's about color because this company want to research the correlation between the color and the number of accidents they involve. That's why one column is color. The second column is always frequency. What does this mean when we look at a table like this? First of all, this blue color car involved in 25 total loss collisions. So if you add all this number together, I already added before I do this video, is 216. That means this insurance company examined 216 total loss collisions. And among those 216 accidents, 25 of them involved blue cars. And that's the meaning of this data. 52 of those accidents involve green cars, and 23 involve these gray cars. So from this table, you can instantly see the highest frequency is 52. That means among 216 car accidents that result in total loss, 52 of those involve green cars. From these numbers, you can see green cars is most likely color that will involve in the total loss collision accident. So that's why we need frequency distribution table. Imagine if you have thousands of these reports, it's not just several dozen of them or 100 of them. You have several thousand, several 10,000 of these numbers, and they put all this number, raw data in front of us. Nobody can tell which color involves the most number of accidents until you organize those data into something such as this frequency distribution table. We can clearly see that green color is the color that's most likely to be involved in a total loss collision accident. Okay, this is called a frequency distribution table. Our purpose for this video is to calculate the relative frequency distribution table. This is called frequency distribution table. Frequency is the actual counts, 25 of them, 52 of them, actual counts. And the relative frequency is a percentage, it's a proportion. For example, if I ask you, among all of these total loss collisions, 216 of them, how many percent of those total loss accidents involve blue cars? Well, you don't know. You have to do the calculation. And that percentage, sometimes represented by a decimal, which is just different format, is called relative frequency. Okay, let's move on to the next page. Now we just introduced this frequency distribution table as a tool to organize data. Actually, there are other tools to do the same thing, to represent frequency distribution, but it's not in the table format. It is in this bar graph format. Let's look at this description of what a bar graph is. A bar graph is a graph that displays a bar for each category. The category, we already mentioned that is the value, the event. With the length of each bar, you can also see the height of each bar, representing the frequency of that category. In other words, for any two-dimensional graph, like this one, you have horizontal axis, you have vertical axis, we call it two-dimensional graph. So in any two-dimensional graphs, and when you do a frequency distribution graph, the horizontal one is always represent the categories or the events. In this case, the first column. So when you use a bar graph to represent frequency distribution, the horizontal one is always equivalent to the first column. And the vertical axis always for the frequency. So always frequency on the vertical axis. If you read these bars, you can see blue one has a height of 25. And if you recall, the frequency for blue car is 25. The frequency for green car is 52. See, this is 50, a little bit higher than 50, 52. So the height in the bar graph represents frequency. And the events is labeled on the horizontal axis. This is just a different format to represent the exact same thing. Okay, now let's look at the next topic, frequency versus relative frequency. I already mentioned a little bit. Let's look at it closely. Frequency represents how many times a certain event occurs. For example, among all of those 216 total loss accidents, and 25 times occurred that involves blue cars. So that 25 is frequency. It is a count, how many times. And relative frequency is proportion. Usually it is represented by a percent or decimal. For example, if I say, hey, totally 13% of all of accidents involve blue color cars, and that 13% is called relative frequency. So just make sure you understand the concepts. And most of the time in real life, actually, relative frequency is more important, more meaningful than the real absolute frequency, than the counts. For example, if we're looking at the total collision accidents within a year for the whole nation, it's not just for a city or for the county, for the whole nation. You know, there's millions of car accidents for sure each year in the United States. That's just a common sense. So many cars, so many people drive cars every day, so many miles, right? So millions of accidents. So that's normal. So we assume there's a lot of total loss accidents. Now, if I say among all of those total loss accidents, there's 25,000 accidents in total loss accidents involve blue cars. After you hear this number 25,000, you will think, wow, blue cars are not good. So many blue cars involved in this total loss accidents. Until I told you that totally they were 1 million, let's assume that number, they were 1 million total loss car accidents. Then you realize, blue cars actually is good. There's not many of them because 25,000 compared to 1 million is really, really small number. That's how important it is for the concept of relative frequency. Relative frequency actually tells you the truth. You don't look at the absolute number. Sure, absolute number sometimes is really big, but look at the whole picture. Look at the total amount first. That's why we need to be able to calculate relative frequency. That's the purpose of this lecture here. Okay, how do we calculate the relative frequencies then? Look at the next page. Now, as you can see, I have exactly the same table that we had in the beginning. This is a frequency distribution table for that different colors of cars. Say we already know there are 216 accidents. If we add the number together, it's totally 216. Now I'm going to write down the formula to calculate the relative frequency first before we do the calculation itself. So relative frequency equals individual frequency, such as 25, this is frequency for blue color, 52, this is individual frequency for green color color car, and such, and divided by the total sum of frequencies. That means you need to add them all together. Total frequency. That's how you calculate relative frequency. When you calculate percent, you always use number divided by total, right? So total frequency, we already did that. So let's say total. We already added together. This is 216. Now, how do we do the relative frequency? Use each of these numbers one by one, divided by 216. And for the demonstration purpose, I'm going to keep 3 decimal digits for the relative frequency. And when you do your homework, make sure you read the requirement. They may require you to have 2, maybe 4, who knows, but you just have to read the requirement. So the first one for us is 25 divided by 216. 25 divided by 216. So I need 3 decimal digits, 0.1157, so 0.116. 0.116, 3 decimal digits. And next one, 52 divided by 216. 0.2407, 0.241. 0.241. Let's take a little bit of time to do this. 41 divided by 216 equals 0.1898, 0.190. 0.190. Make sure you input 0 if they require that you have 3 decimal digits. 36 divided by 216. 1666, 0.167, 0.167, and 39 divided by 216. 0.181. 0.181. Last one, 23 divided by 216. And this is 0.106. 0.106. Now, these numbers are called relative frequency. So what does this mean? If you convert these numbers to percent by moving decimal digit to the right two places, the first one will become 11.6. So instead of saying there are 25 cars, blue cars involved in the total loss accidents among 216 of them, you could say they are 11.6% of all of the total loss accidents occur to blue cars, involve blue cars. Or we can say 24.1% of the total loss accidents involve green cars. So almost 1/4 of the whole thing, almost 25%. That doesn't sound good, right? For this green color cars. Okay, now I'm going to add all of these numbers together to get a total sum of relative frequencies. So before I do that though, let's guess what number we're going to have. What number is expected? Think about that. This is relative frequency relative to the whole thing. Whole thing is 216. We get this number by using each of this number divided by 216. Now we want to add all this number together, and these numbers come from all of these numbers doing division. So if we add this number together is 216, then divided by 216, that is the number divided by itself. It will be 1. So that means we should get 1 if we add them all together. Do we really going to get excuse me, let me drink some water. Are we really going to get 1 exactly? Very unlikely. The reason is that each number is a rounded number. You have a rounding error in each number. So when you add them together, very likely you get something that is not exactly 1, but should be very, very close to 1, because theoretical value should be 1. Since you have rounding error, you could get something close to 1, little bit lower than 1 maybe, little bit higher than 1 maybe, but it's not going to be far away from 1. If it is far away from 1, something is really wrong. So let's just add them together actually to see what we get. We could get exactly 1 though, but the chance is very low. That is pure luck. Plus 0.241 plus 0.190 and plus 0.167 plus 0.181 plus 0.106. See, we get a total relative frequency 1.001. The rest are zeros. We take 3 decimal digits. As I said, we expect something very close to 1, but not exactly 1. If you got exactly 1, again, that's just luck. But it cannot be farther away from 1. 1.1, 1.2, something wrong. Or 0.9 is wrong. 0.98, 0.99, that's fine. But one thing I like to mention that when you do your homework, they could ask you what is the total sum of relative frequency, even though based on your own calculation, you got something really close to 1. But when you enter the answer, make sure you enter exactly 1. Don't use this 0.001. Because theoretically, no matter what data you have, the total sum of relative frequency is always 1, exactly 1. That's why even though your calculation gives you something that is close to 1, but not exactly 1, you still put 1 as an answer on that page. So just I want to make it clear. And something else I like to mention here after you understand this basic procedure. Imagine if you don't have 6 numbers, we only have 6 numbers to do the division to get six relative frequencies. How about you have 60 of this? You have to repeat this individual division one by one do this division 60 times. How about you have 600 numbers, 6,000 numbers? Do you want to do 6,000 divisions one by hand, or even use a calculator? You don't want to do that. It's just too tedious. So now I'm going to show you how to do this using Excel. It's not required, but just for those who want to learn how to do Excel, using Excel to do that faster, you can see it really fast. Okay, I already have this Excel prepared to save some time because I'm doing this video. Now you already have this frequency distribution table. So now I need to calculate total frequency first before we do division. So in Excel, whenever you do any calculation, you have to start with equal sign. So I type equal sign. Now I'm supposed to add them together. How do I add them together? I use a function called sum, S-U-M. Then open the parentheses and input all these numbers, select this, and close the parentheses. That's all you need to do, no matter how many numbers involved. Hit enter, you know that's correct. We have 216 total number of car accidents. Now it's time to calculate the relative frequency. Okay, now I am supposed to use each one of these frequencies divided by 216. Now, sure, you can do the division one by one. Say, for example, this equals 25. Just click 25 slash, which means division. Click 216, then enter. You got this number, round it, you got 0.116. That's the correct answer. And do the second one equals 52. Click slash 216. You got a second one, and so on. But this is not the way I want to show you. It's not the way we do it. The reason is very simple. Again, if you have 6,000 of this, you still need to do it 6,000 times. What's the point then? There's not much advantage compared to using calculator. So we don't do it that way, even though you can, but we don't do it that way. It's not efficient. So I'm going to erase this and do it again. Now this is what you do. Watch this closely. Equals. First one, still the same thing. Click this slash 2016. Now don't hit enter yet. Now you want to use each of these numbers divided by the same 216. That's why you need to tell Excel you want to use these numbers one by one, but you don't want to change the number on the bottom. How do you tell Excel that? You do that by insert a $sign in front of this letter, in a $sign in front of this number. You can do it by using a shortcut. If you use a Windows machine, just type, when this cursor still blinking, just type F4 button, F4. You see that? A $sign in front of letter, a $sign in front of this number. Now, if you don't have that button, if that button doesn't work for you for some reason, you can manually type this $sign in front of letter and number. It still works. So enter. I get exact same number, right? Now, the beautiful part is that you don't need to do the rest. Even if you have 1 million of this, just one click to get them all done. How do we do that? This is how I do that. After you finish the first one, click on it, highlight it, so that you see the small square down here and here. See, when I move it, the cursor becomes narrower. See that? And double click quickly. That's all numbers you need. No matter how many. Now, if you can manually run this to the 3 decimal digits, or you can use another function if you want, up to you, but you already got relative frequency. If I use a function, it's called round, to do rounding. Round. Then you need to tell Excel what number you want to do rounding. You select this first one, you want to do this one, and a comma. Look at the prompt here. You need a number, which is this, comma, a number of digits. They ask you how many digits you want to have, how many decimal digits. I want 3 this time. And close it. What I get? 0.116. And you know that's correct. And what do we do next? Again, double click. I got all of this. Now, Let's do total relative frequency. This is relative frequency. Again, how do I total? Still remember? I do a sum, right? Add them together. To say if we get 1.001, because I got that by doing it on paper. Enter 1.001. How about if I do the same thing using this relative frequencies? These are numbers without rounding, even though they only display like 8 digits, 9 digits, but there are thousands of digits after this. They just don't display all of them. That means there's no rounding here. So if we add them together, we should get exactly 1 to be right, because it's theoretically supposed to be 1. What do we get? Exactly 1. I hope this makes sense to you. Now we're going to do another example, but this example is like from ground up. That means we are not given a frequency distribution table to start with. We are given just a bunch of data. We need to create a frequency distribution table by ourselves and then calculate the relative frequencies. So let's do that. So this is our example. Now let's read it. Suppose the requirement is that create a frequency distribution table and calculate the relative frequencies. And suppose, turn the camera a little bit. Suppose, for example, that researchers are interested in determining the age at which adolescent males show the greatest rate of physical growth. A random sample, for the moment, don't worry about this word random sample. You're going to learn that when we do statistics. You just need to know there are 35 boys. That's all you need. A random sample of 35 10-year-old boys is measured for height and then remeasured each year until they reach 18. Basically, it goes like this. You have 35 10-year-old boy, and you're going to measure their height each year. Say measure their height at 10 years old, measure their height at 11 years old, 12-year-old, until they reach 18 years old. They do measurement each year for each boy. They record their height so that they can determine at which age for each boy they grew fastest. That's their purpose. So last sentence is that the age of maximum yearly growth for each subject is as follows. I don't like this word subject, by the way, because it's not like not an item, it's a person. So I rather say for each boy, but either way is okay. So basically we are given this the age of maximum yearly growth for each boy below. So what does it mean, all these numbers? For example, the first one, 12. What does that mean? That's age. In other words, for that particular boy, he grew the fastest at age 12. Age 12. Second number is 14. That means the other boy, whoever is, the other boy grew fastest at age 14, and so on. So this number represents age at which maximum physical growth happened. Now, how many numbers do we have? Actually, if you count it, it's 35. Not surprised, because they measure 35 boys. Each boy has this particular age at which he grew fastest. So this totally makes sense. Now the thing is, in order to understand what age in general people grew fastest, what age they grew maybe slowest, if we need that data, we have to organize this data. It's already a small big mass. Small big mass, that's what I just invented. But it's a sort of mass because you cannot tell much about this data. We only have 35. What if you have 350 of these numbers? How about 35,000 of this kind of numbers? Nobody can tell anything from it. That's why we need frequency distribution table. Try to organize data first. So again, at this point, everybody can do that. This age, this numbers itself are values, should be in the first column. And how often each number occurs is called frequency, should be in the second column. So we're going to do that. Literally, we're going to do that. So let's say the smallest age is 10. I already lined them up. Everybody can identify smallest age and highest age. That's not an issue. So that's why I already put it in the first column. Let's count for each one to see what do we get. The smallest number is 10. How many 10 they have? This is 1, just 1 10. So this is 1. 11, 1, 2, 11 just 2. So hopefully I didn't count it wrong. 12, 1, 2, 3, 4, 5, 5 12s. And 13, 1, 2, 3, 4, 5, 6, 7 13s. And 14, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 14s. And 15, 5, 5, 1, 2, 3, 4, 5, 6. And 16, 1, 2, 3, 3, 16. 17, this is 7, 7, 7, 7, no more 7, just 1. 18, 8, 8, 8, 1, 8, just 1 8. How do I know my count actually was right? My counting was right. So if I was right, if I add them all together, it should be 35 because total number of 35. So the total number of boys is 35. It's just only one boy grew fastest as 10 years old, and 9 people grew fastest at 14 years old. So total has to be number of boys. If I add them together, and let's say 3, 8, 15, 24, 30, 38. Now let's do it again. 3, 8, 15, 24, 30. Apparently I did something wrong. This 38 is supposed to 35. Let's do it again. Number 10. Number 10 is 1. That's right. Number 11. Slow down a little bit this time. 11 is 2. Still right. Number 12. 1, 2, 3, 4, 5. 5, 12. Still good. 13. 1, 2, 3, 4, 5, 6, 7. 7, 13. Still good. 14. 1, 2, 3, 4, 5, 6, 7, 8, 9. Still good. And 15. 15. 1, 2, 3, 4, 5, 6. Yeah, 6, 15. Still good. 16. 1, 2, 3. There's only 3, 16. Let's do it again. 1, 2, 3. Yes, I don't know why I wrote 6, 3. This should be right. Let's do it again. This is 3, 8, 15, 24, 30, 35. So that's right. So we got total frequency is 35. Now we can do relative frequency. Let's do it using Excel again. And it's faster. So I already created this frequency table. So now we do a total here. Just go through this process again. This is total. So you can see how Excel works. So I'm going to add all of these frequencies together. That's supposed to be 35. Yeah, it is. Then I calculate the relative frequency equals this number divided by, and this number using F4 button, so that it divided by the same number again, and double click. Yeah, that's the answer. Again, if we want to have 3 decimal digits, we can do rounding. Round. Select the first number, comma, and tell Excel how many decimal digits you want, and close it, enter. and then double click to get all of this around it. Yeah. So that's it. That's this section. And in the next video, we are going to talk about how to create bar graphs and pie graphs using Excel. So until then,